It's terrific to be here. I am delighted to be on day 5 of my 4-week trip, and already I'm energized and excited to be talking with a lot of you. So I'm making my rounds and really enjoying my trip. In trying to decide what to talk about today, I needed to choose one thing. I thought about 2 or 3, and it's Friday afternoon, so I'm just going to tell you one story about radiocarbon. But we have measured other isotopes, as Sue mentioned in the introduction. Nitrous oxide, that does some chemistry. I'd love to talk with people about what we've learned about N2O and our measurements from Fern air and air that goes back to 1978 at Cape Grim in Tasmania and Australia. We've done methane, molecular hydrogen, various isotopes of CO2, including radiocarbon, and these have all come in a long-term collaboration with Sue Schaffler and Elliot Atlas and the many whole air samplers that there are here at NCAR. That's been an incredibly important part of the research that I started at UC Berkeley as an assistant professor 20 years ago. And so here are Elliot and Sue. They have gone out and collected whole air samples, measured them for a multitude of things, and then sent them to my UC Berkeley lab so that we can measure many different isotopic species. And I will say a lot of these measurements that we've made, we need the whole air samplers. We can't do these in situ. And in fact, even in the 1990s, there was a revolution in isotope ratio mass spectrometry where we could do it in continuous flow and feed things in from a GC, that instead of needing hundreds or thousands, or in the case of molecular hydrogen, 40,000 liters of air for one sample, right? We could get a liter of air and make all of these measurements on them. So, so it was really that revolution. We're maybe at the dawn of being able to measure isotopes. I mean, that can be done for water isotopes in situ, and maybe some other species. Maybe we're at the dawn of that next revolution to be able to measure the isotopic compositions in situ. But it's going to be a while, and in addition to that, some of these we may never be able to measure. I also archive a lot of these whole air samples. I have 500 samples archived in my UC Berkeley lab that go back to 1997. Maybe I want to put that out there and remind people that if there's something that is stable in a glass flask, that I worked very hard with Peter Tons 20 years ago to make sure they'd be as stable as possible. If there's something that we can measure now, I have a 20-year record of stratospheric and some upper tropospheric air. So I'm trying to make sure that we get as much scientific bang for the buck for these whole air samples. So into the foreseeable future, these whole air samplers are really important, and we can do some cutting edge science as more and more things become possible to measure. Okay, so I needed to pick out one thing today to tell you a Friday afternoon story, and that would be radiocarbon, the radiocarbon content of stratospheric CO2 in particular. Okay? So I want to take a new look at old air, and that will become clear, I hope, as I go through my talk. What do I mean by that? A new look at old air in the stratosphere by looking at radiocarbon. So I'm going to start with, I'm going to use this analog pointer because that's less likely to advance the presentation. If anybody is listening offline, sorry about that. I am using an analog pointer to point to the first bullet here. First of all, I want to make sure everybody's on the same page. I want to talk about how radiocarbon is produced in the stratosphere and the upper troposphere, both from cosmic rays and nuclear weapons. And the so-called bomb radiocarbon data, as many of you probably know, was used to look at the stratospheric circulation early on and has many applications in the carbon cycle. But what we've done with the whole air samplers from Elliot and Sue is we've been able to make the first extensive set of stratospheric radiocarbon measurements in what I call the post-bomb era, right? I used to call it the post-bomb era, and then I realized that's when the bombs went off, is the post-bomb era. So it's the post-bomb era and what some of their applications are. And in particular, I want to touch on these two. The radiocarbon measurements that we've made and comparisons with some model results show that the radiocarbon levels are exquisitely sensitive to the transport schemes that are put into stratospheric models. And a comparison of the residence times from radiocarbon and stratospheric mean ages from other sources such as from CO2 and SF6 concentrations, right, may really help us diagnose more details of the stratospheric circulation and whether it may be speeding up as climate is changing. And then in the last few minutes, I'm also going to show you some applications that are important in carbon cycle studies. We can take our stratospheric observations and empirically, with very little knowledge, calculate the global radiocarbon production rate and the global annual mean net 14 CO2 flux to the troposphere, which is really relevant and becoming more relevant in the future as the bomb radiocarbon pulse continues to decay away into the ocean and then ultimately coming back up from the ocean. So that's an overview of what I want to talk about today. So as promised, right, carbon-14 atoms are produced by nuclear spallation reactions, the capture of a thermal neutron that has the right energy to be captured by a nitrogen-14 nucleus, right, producing radiocarbon. The radiocarbon atoms have a half-life of almost 6,000 years. So for the stratospheric circulation, we don't have to worry about that, okay? Then these atoms, with this half-life that we get to ignore, the atoms are then oxidized to 14CO and then to 14CO2 on the time scale of about 3 months. Okay? Neutrons also came. Neutrons, then where do these thermalized neutrons come from? They come from the cascade of particles from incoming galactic cosmic rays. So this is called the cosmogenic production, right? So these protons and neutrons and alpha particles are coming in from galactic cosmic rays, and they need to get all the way down into the lower stratosphere and upper troposphere through this cascading process before they have the right energy to be captured by the nitrogen nucleus, okay? So this production rate, okay, those energetics means that the production rate maximizes in the extratropical lower stratosphere and upper troposphere, because that's one source of neutrons that we're particularly interested in. But atmospheric nuclear weapons were also a source of neutrons from the atmospheric testing in the 1950s and the 1960s. So that's what produced that big bomb pulse of radiocarbon during that time period. And this is what that looks like. Here's the pulse, right? People were measuring radiocarbon on SOOS. Ultimately, UCSD, as a function of time, was measuring it. Here's the period of the strongest bomb tests here in red, and then we see this tremendous spike, and then that decayed away, right, as it was transported throughout the stratosphere and then down into the troposphere. You see some interesting spikes here. And then it decays away as that radiocarbon originally in the atmosphere and the stratosphere then is taken up by the various carbon reservoirs in the ocean, terrestrial biosphere, et cetera. Okay? And so the last extensive radiocarbon measurements to be made in the stratosphere were made out to 1974. Right, and from that, a lot of information could be derived from stratospheric transport rates, and some people who may be in the audience have worked on this. Everything I'm going to talk about, everything I could talk about, there's somebody in the audience who knows something about this, so that's also the fun of being here as well. So again, to show you the stratospheric circulation, from the nuclear weapons tests in the tropics, well, lo and behold, fallout was coming down in Washington, D.C. and Boston. Right, even though it was way down in the tropics. So we learned a lot about stratospheric circulation from that. And there was a big effort to go collect hundreds of liters of air per sample for radiocarbon measurements from the WB-57 and from stratospheric balloons. And I'm going to show you what some of that data looks like, interpolated by Hal Johnston and worked on, I'm sure, by Doug Kinnison. I'm going to show you sort of the interpolated measurements from the balloon and stratospheric aircraft measurements. This is showing data in red from October 1963. I'm going to show you a poor professor's movie, okay? I knew this would work no matter what PC or Mac I needed to work on. Okay, here's the poor professor's movie. I'm just going to advance the slides to show you the time series. Okay, and so the data, again, are Hal Johnston and Doug Kinnison's worked on this. These are the model in blue is some unpublished results from Livermore's 2D model. We didn't feel at the time we had enough constraints to have this work out, but at least you'll be able to see this when I hit the advance button. The movie starts here. I have to keep hitting the advance button here. So that was October 1963. You can see that radiocarbon in the lower stratosphere. That's a year later, not October 64, October 65. Here's April and finally November. So we can also go backwards. There we go. Okay, right? This is to give you a sense of what the bomb pulse of radiocarbon did in the stratosphere. Okay, but 1974 were the last measurements. They were relatively sparse, like in situ measurements tend to be. In situ meaning these were grab samples anyway, but they were still in space and time rather sparse. They weren't trusted. One of the reasons they weren't trusted, and I'm going to come back to this later, is because nobody's 1D or 2D model, which was state-of-the-art in the 70s, could reproduce the data that the models, the 1D and 2D models in the 70s were flushing air too fast out of the stratosphere. Remember that. I'm going to come back to that for the 90s as well. And they were sparse, and really there were no modern ideas of how to compare tracer-tracer correlations that you might get with a global model. Okay, so they really weren't trusted. There's some other interesting ideas about radiocarbon measurements at the surface. People also didn't know in the 60s and 70s about the rectifier effect. So I won't take the time to do that today, but what people were measuring at the surface seemed to indicate that the stratospheric measurements were wrong. So there's an interesting story about that. I could talk to you about that later too. Okay, but that's what was done. The last measurements were made in 1974. The Japanese from a balloon whole air sample have 14 measurements from the 90s, but they weren't sure what to do with them. All right. So, but then again, the other application, right? These radiocarbon measurements then in the atmosphere, also measured in oceans, soils, plants, and other carbon reservoirs, were used to quantify the inventories, the residence times, and the gross fluxes of carbon in and between these reservoirs. Okay, this really powerful tool. Also, CO2 has no radiocarbon because it's kind of the fossil carbon, right? It's all decayed away. And so again, using this radiocarbon measurements and the redistribution in all of these reservoirs is also a way that people are actively working to quantify anthropogenic CO2 emissions, for example. So there are these applications of the bomb radiocarbon. So when I realized we had enough air left over in the whole air samplers, that, as I'll show in just a moment, and I've been deeply interested in stratospheric transport and having new constraints on stratospheric details and rates of stratospheric transport. I thought, well, what could we do with a new set of 14 CO2 measurements? What could they reveal about stratospheric transport, stratope exchange, and its influence on surface levels of 14 CO2? Okay, voila. The cryogenic whole air sampler was first tested in the fall of 2003 by some balloon flights out of Fort Sumner, New Mexico. So this is showing the balloon at dawn. Here is the gondola here, and for scale, here's Rich Lube, conveniently, right there, there's Rich. And then here's a picture of the cryogenic whole air sampler. This was based on some designs that had been used earlier back in the 1960s, but this was updated for a new cryogenic whole air sampler. So here's a picture of this. There are 26, I believe, 800 milliliter canisters, which have a gold finger with liquid neon inside, okay? And so they're evacuated. When it's opened up, then they capture the whole air sample. Maybe not a little hydrogen or helium, but I'm not trying to do hydrogen and helium isotopes on these, right? Okay, and so then what we had done, so all kinds of trace species were measured, okay, by the whole air sampler group. And then we could extract the CO2 from the samples. We then graphitize them at Lawrence Livermore and run them at the Center for Accelerator Mass Spectrometry to measure radiocarbon. And this is a warehouse-sized measurement technique, by the way. This is definitely not in situ technique. Okay, you can't fly this. And so what I'm showing then here is the capital delta 14 carbon. That's a measure of the ratio of 14 CO2 to 12 CO2 relative to a standard. It's in per mil. That's the part per thousand deviation of a sample from a standard. And the precision is about plus or minus 1 per mil. That's smaller than the size of the samples that symbol sizes that I selected here. Okay, so the test test flight was in fall of 2003 of this new cryogenic whole air sampler, and also other flights in fall of 2004 and fall of 2005. So here's the radiocarbon content. Here's a vertical profile versus altitude. Here's 2003, 2004, and 2005. So as we might expect, right, as we move into the stratosphere, the radiocarbon levels are growing. Okay, so here's the same plot here. Here's the simultaneous measurements, right, from the whole air sample of N2O to give some perspective, right? So N2O is photolized and photooxidized. Here's the troposphere, right? As we move up into older air, older photochemically processed air, we're seeing the radiocarbon content increase. My favorite way, of course, since the 90s, is to plot long-lived tracer versus a long-lived tracer. And that would be to use N2O as my x-axis here. So here's radiocarbon versus nitrous oxide. We can see this growing in. We see a more compact relationship, right, where some of these, which may be filaments of air from a more polar latitude, we might guess from here then, a lot of that variability can drop out as we look at this. Okay, so what can we learn from this? These are the first measurements of radiocarbon in the stratosphere since the stratosphere has purged itself effectively of the original bomb radiocarbon. Some of it may be recirculating, but what we can see from the tracer-tracer relationships is the radiocarbon, as anticipated, is a long-lived tracer with a stratospheric source. What we can see from the different years is the so-called SOOS effect, which if you don't know what that is, I'll show that in the next slide. The SOOS effect propagates into the stratosphere, where the radiocarbon propagating up from the troposphere, there's less and less due to the emissions of fossil fuel, CO2, right? So here's the SOOS effect. The SOOS effect is the smoking gun for anthropogenic CO2. It's the isotopic fingerprint that proves that this is coming from humans. So here is a time series at La Jolla, California. This is from Ralph Keeling's group, radiocarbon versus time from 1992 to 2008. Okay? And so this decrease, especially recently, is due largely just to anthropogenic emissions. But it's about -5 to about -10 per mil now in this later time period of the record. So as CO2 is increasing, the radiocarbon content is decreasing due to the lack of radiocarbon in the fossil fuels. Okay? So we can see that then propagating from the troposphere into the stratosphere. Okay? Again, we see 2003, 2004, and then 2005. Okay? Then, as I mentioned a little earlier, we also can see the filaments of air from higher and lower latitudes. So we're not as worried as people were before they had simultaneous measurements and looking at the original bomb radiocarbon, where you might measure something from a balloon over the US, but you wouldn't know if it was more polar-like or more tropical-like, and that was really confounding. But the beauty of tracer-tracer correlations, at least in the stratosphere, right, where things are much simpler, we can denote what was more characteristic of a higher latitude or a lower latitude. Okay, since we didn't know quite what to expect from radiocarbon, though. We also could compare our results here with 3D model results in which we put, which we implemented a radiocarbon production. Okay, and so this was, I had worked with Lawrence Livermore National Lab, Philip Cameron Smith. One of my students was able to implement this. Their 3D chemical transport model impact, let's see, integrated massively parallel atmospheric chemistry transport model, okay? And I'm showing some results there using MACCM3 meteorology for 1997, repeated over and over again. So we're not trying to recreate the filaments here, we're trying to understand what we've got in radiocarbon with this tracer. So these are really busy plots, but again, here's what you'd seen earlier on the left. Here's radiocarbon, the vertical profile of radiocarbon, the vertical profile of nitrous oxide, and here the radiocarbon versus N2O, all right? And the colors are the different years, just as before. And so these are the model predictions. And from this then, we can see that, right, here's more tropical, here's 2 degrees north model results, here's 89 degrees north here, okay? So that we can see if we intercept as the balloon is taking a vertical profile, right, over one location, okay, more tropical filaments of air will pull the radiocarbon this way, more polar should pull it this way, okay? So that's one of the things that we could use the model results for. Likewise for N2O. And then likewise for here, more polars pulling it this way, filaments of air, more tropical is pulling this radiocarbon into a relationship down. So a combination of the observations plus the model results shows that the radiocarbon in the stratosphere, now that there's no longer any bomb radiocarbon, first generation if you will, is determined by the latitude and altitude of the production, okay, by stratospheric transport, that redistribution, and then by strat-trop exchange. So for strat-trop exchange, we see the SOOS effect coming in, and then we see the transport, we infer the transports going out, okay? All right. What I'm particularly interested in is in the busyness of this slide. The predicted radiocarbon levels, right, are very sensitive to the meteorology that's used in the chemical transport model runs that we've done so far. Okay, so now you see the same data as a function of the color as a function of time, but now we see model results for northern mid-latitudes just for the 2004 data in blue, so we're just comparing it with that. But the interannual variability is interesting to look at here too with respect to that being much smaller than the model results. So here we see, right, this higher level predicting a very high level of radiocarbon, right? That's from the finite volume community climate model, meteorological fields input into the model. Here's the middle atmosphere, the MACCM3, which I'd shown you earlier, these results, and then finally the finite volume data assimilation system set up here. Data assimilation just for the winds, not for radiocarbon, okay? And it's known from other studies that this transport gives mean ages that are much higher than observations and that we think are accurate. This gives mean ages that are much too low, and the MACCM3 gives the most reasonable mean ages, okay? And in fact, that's what we might see from, right, if the mean ages are too high, they're too large, it allows radiocarbon to accumulate too much, right, and vice versa. But it's exquisitely sensitive to that. Right? It's so sensitive to that it dwarfs the SOOS effect, it dwarfs filaments and kind of variability that we might see in some of these profiles. So my colleagues and I found this very promising, that we may be able to use these and additional observations to provide new constraints on the stratospheric circulation and how that stratospheric circulation may be changing over time. And how well models are doing with respect to these observations. So I want to take a little detour into an old look at old air in the stratosphere, sort of. Again, I feel like I am preaching to the choir, bringing coals to Newcastle, let's see, but maybe not everybody has taken an old look at old air in the stratosphere. So I want to give a detour on this to motivate this, and I think to drive home where I think some interesting model measurement comparisons might be, okay? So here's the old look at old air in the stratosphere. The mean age is from CO2. So Sue said I was at Harvard and I was in the field for so long, right? About here, I just moved in with my cat sitters because I couldn't move into a hotel, which would have been fine because I had cats. But I just moved in with my cat sitters because I was in the field 2/3 of the time, looking at new air in the stratosphere and old in the stratosphere. So here is the CO2 concentration as a function of time. These dots are when I was flying my in situ CO2 instrument on the ER2. This is for the newest air in the stratosphere based on A, being above the tropopause, and B, other tracers. So this is the new air that we measured. And I noticed about here, after we'd flown about 3 times, that serendipitously we could link the stratospheric boundary condition to an average of Mauna Loa and Samoa delayed by 2 months. Right, and except in really weird situations, that's our boundary condition, right, is right there. And we can linearize it and just try to see then, develop observation mean age of air for a given location and time in the stratosphere. So we measure all over the place, and then from the time lag between the measured CO2 concentration and that stratospheric boundary condition, then we can determine a mean age. So here's CO2 concentrations, here's time, here are all the times I'm in the field again. Arlen took over here, okay, I went to Berkeley here, so these are Arlen Andrews points here. But we can take the time delay back to the linearized boundary condition and show that at each step of the way over this time period, the air at about 20 kilometers at mid-latitudes, right, is about 3.5 years old. Okay, we've taken methane oxidation into account, because they're simultaneous measurements of methane. All right, so that's how we can get a mean age of air. Then we could look at these versus models that were state-of-the-art 20 years ago. Okay, so here is the mean age versus latitude. I told you how much time I spent in the field, right, to get this latitude range here. Here's the mean age from CO2. We have similar mean ages, except when the mesosphere is getting in the way for SF6 mean ages from Jim Elkins, right, at NOAA, who was also on these flights. This other green swath is the majority of 2D and 3D models, okay, at the time, right? So we can see that the air is much older than predicted by models. In fact, they're older by a factor of 2 or 3. There are a few outliers, but modelers at the time would say, oh, I don't believe that model anyway. Okay, so this is the swath of believable models at the time. So we also had ballooning measurements. Again, the age of air being considerably older than what models predicted at the tropics, at mid-latitudes and high latitudes. Okay? So these are little, for those of you interested, these are little filaments of polar vortex air that hung around in the summer that we could intercept, right? So we're not, but you can extrapolate to where we can see from other tracers that it would be more normal air. Okay, so that was 20 years ago. But this slide, I want to show you how important, I think, I guess it's my work, so I should be a little bit careful, but I'm even going to call it transformative, that the CO2 measurements and the SF6 measurements that Jim Elkins' group had made were really transformative in modelers going back and seeing, what is the problem, all right? And so I'm going to show you an update, again, which some people in the audience and some people that I'll talk to later who I couldn't be here, right? Recent publications from Kovacs and Dietmüller et al. So Rolando's in this and Doug is in these. I tried to make them sort of the same scale, right, to show you the observations or whatnot, right? We don't see this huge discrepancy of a factor of 2 or 3 anymore in what model mean ages are. And there's Wacom ages in here, et cetera, right? Okay, so there was the constraints that came from 20 years ago have really improved the mean age of stratospheric air from those measurements, okay? But there is still an interesting mystery that is beyond, I think, what we know well now and what's motivating me to continue, right? This is not the be all and end all, because the next interesting puzzle for me, thinking about how can we measure aspects of the stratospheric circulation that are important, then this next one is, well, in the meantime, while I've been doing other isotopes at Berkeley, not quite radiocarbon, but this is why I got very interested in the radiocarbon, chemistry climate models predict an acceleration of the stratospheric circulation due to changes in radiative force and in ozone loss, okay? And I'm sorry if your publication is not up there, but I only had so much room. All right, and yet, we're not seeing that yet in the observations. And perhaps it's in the noise of the observations, but that's why I'm motivated to make more measurements so that we can get the signal out of the noise. So again, to show you mean ages from CO2 from this time lag again, now this is at 25 to 30 kilometers at mid-latitudes, we can see data that actually goes all the way back to 1996, and we see this mean age of 4.5 years from 25 to 30 kilometers. This is just for CO2. We can add SF6 and other groups in. It doesn't look, we can't see that it is accelerating or changing. Here are mean ages from CO2 and SF6 with these different, I'm a co-author on the Angle paper putting together all of the stratospheric observations, mid-latitude, northern hemisphere, okay, in a particular place over this time. And maybe in the noise, we're not seeing an acceleration over the 30 years of this data set. And then this was just updated recently by Angle with some new measurements. I believe these are from SF6. And again, I've squished it to try to give you this so you can do a one-to-one comparison on the same scale with those. So we're not seeing that yet. So of course there's some complications. So Rolando and Bill and Doug did probably what I'm guessing is an Aussie, right? They put real tracers into the model, and the fact that they're real tracers and we are undersampling. Yeah. Please, NSF and NASA, give me more money so we're not undersampling the atmosphere, right? Okay, so undersampling, I'm the first to agree with that. We're undersampling. May render a trend being in the noise. That's a rather awkward way of saying it. If there's a signal, it's in the noise, right? And others, again, in this room, looking at ozone trends, water vapor trends, temperature trends, and other observations over these same time periods, it's all a little ambiguous. Maybe the lower branch of the stratospheric circulation is speeding up. Maybe we're just not seeing it with these mean ages in the middle atmosphere. What's the upper branch doing? What's the lower branch doing? Ozone and water vapor are pretty complicated also. So there are all these different possible trends. It's ambiguous, all right? And for those of you who are not working on this, I wanted to give a little plug for why do we care here, okay? We're not seeing a signal in the noise, perhaps if there is a signal. Okay, what I find intriguing about it is this is the one climate change signal that is robustly predicted across models, right? But it hasn't yet been observed, okay? So to me, that's pretty interesting, right? Pretty much every other robust climate change signal we are witnessing, we are seeing there's evidence for. But it also has lots of effects. It will affect the timing. The changes in the Brewer-Dobson circulation may affect the timing of the Antarctic ozone hole recovery, as well as the lifetime of ozone-depleting substances. The dynamic coupling between the stratosphere and the troposphere can have an effect on weather and climate. There are other climate feedbacks, such as changes from the circulation-induced changes in upper tropospheric water and ozone, and a changing stratospheric contribution to surface ozone may have implications. Hey, maybe for Bakersfield, they can't blame their ozone exceedances on China, but maybe they'll start blaming it on the stratosphere. Maybe they already do, and potential human health effects. So it's an interesting signal, fundamentally from a scientific perspective, but there are also implications for us down here in the troposphere. Okay, and so I want to take a few moments then to say why more data and new tracer data, in addition to not just the mean ages, but something that may have a different sensitivity to circulation changes in different regions of the stratosphere, radiocarbon can help. So now, that was an old look at old air in the stratosphere. So here's my argument for the new look at old air in the stratosphere. So we want to radiocarbon date the stratosphere with the measurements that we have, and then with continuing new measurements of radiocarbon. So what are the differences with the mean ages from CO2 and SF6 with the radiocarbon? Well, radiocarbon has a lower stratospheric source and a tropospheric sink. That's different from the tropospheric source gases, CO2 and SF6. And in fact, the radiocarbon is a tracer that's more like a proxy for the residence time instead of a mean age tracer. Okay, why does that matter? Okay, well, let me define these. The mean age is an average over the ensemble of transit times from the tropical tropopause to a point in the stratosphere, right? We know that tropopause boundary condition for CO2 mixing ratios. We can give you a mean age, the average, right? There's an average, the mean age, and then there's a width to that and a long tail, but we can give you the mean age from that. The residence time would be an average over the ensemble of transit times from that point in the stratosphere that we make a radiocarbon measurement to the tropopause. Okay? And what would be the difference? Well, they certainly are correlated, right? But they have a different sensitivity to aspects of the stratospheric circulation. So I'm taking the information that Hall and Waugh had done. They'd compared a bunch of, again, state-of-the-art in the year 2000 2D and 3D models with a tropical pipe model analysis so they could understand a little bit about the transport rates. And they found that the mean age and the residence time are related. If you sped up the stratospheric circulation, right, the mean age would decrease. That means if you increase the vertical velocity, the mean age decreased. The mean age could decrease if you decrease the amount of recirculation of mid-latitude air into the tropical upwelling region. That's the detrainment flux, right? The mean age would decrease because that long tail of ages that'd be headed out of the stratosphere instead of up, over, and around, okay? And if you would also, in these models, decrease the mean age if you increased the area of tropical upwelling area, for example. So all of those things in these models, decrease the mean age, but for given mean age, the residence times were highly variable for different models, okay? So they're correlated, and I decided not to show you a scatter plot. I can show it to you later if you're interested in, but there's not a one-to-one correlation between mean age and residence time in the models. So they're different. The residence, right, if we're looking at the residence time versus mean age, we may be sensitive to different parts of the circulation, like something in the lower branch, for example, or what's going on with those balloon measurements at 25 to 30 kilometers. Why are we not seeing a trend there? Is it just in the noise, or is that a sort of node with respect to where the changes are actually occurring, okay? So we do have, oh, the Rockies game started, guys. If you want to check your phone, it's okay with me, okay? It's all right with me. Yeah, I was checking the Warriors, Cavaliers. Yeah, just talk faster. Okay, good. All right, so check it. I'll keep talking. Okay, so, but we do have more measurements. These are a lot of new measurements. Actually, just let's take a trip down nostalgia lane here and go back to Polaris, 1997, okay? Solve, Pre-Ave, these balloon flights that I've been showing you, DC-3, Seekers. One of my students is right now working on atom 4 samples from the stratosphere, okay? So we're getting to have a long time series of measurements of the radiocarbon. Here's versus altitude, it's a mess. Here's radiocarbon versus N2O, right? Where again, we see the SOOS effect, right? But we're getting to have a lot of data over time, and we'd like to continue this into the future as well. I'll end this part here, and I'll do radiocarbon production super fast after this. We will need to compare the stratospheric radiocarbon with model results, I believe, right? Remember I'd shown you I could just say from the stratospheric boundary condition, I can give you a mean age, I can think about mean age independent of a model result, right? I'm not sure we can do that for the residence times because I'm not sure how to calculate one without help from various models, right? There's no easy reference point like there was for the mean ages. So here I am calling all modelers, right? To make comparisons, maybe help me figure out how, can we do this empirically? I mean, I could give you a residence time for the stratosphere. Half of you guys could probably too. I don't want a mean residence time for the whole stratosphere. I want a mean residence time at this location in the stratosphere and that. So I'm not sure what our exiting boundary condition would be. So I think this is a highly sensitive diagnostic, but it's going to be in the comparisons with models and figure out what models are doing differently with respect to the observations, okay? So I would love to have these go into Wacom in addition to the Livermore model and et cetera, okay? So I can't show you a pretty plot of residence time versus location, but I think it's going to be a powerful way of diagnosing stratospheric transport, all right? Okay, so in the last couple of minutes, yes? How are we doing? Okay. In the last few minutes then, so we finished sensitivity to the stratospheric circulation that I wanted to get across to you, right? And a comparison of the complementarity of stratospheric mean ages and residence times. But in the last few minutes, especially for people who may be working on carbon cycle dynamics or know people here who do, and I've been talking with some of them too, we can get an empirical estimate of the global radiocarbon production rate, the cosmogenic production rate, to compare with the other ways that people have calculated in the past, as well as a global annual mean net radiocarbon flux to the troposphere. And these are needed more and more, actually, for carbon cycle studies, okay? All right, so let's see. That's what I'm going to talk about now. All right, this is the bottom line, and then for those of you who don't already get this immediately, I'll show you a few plots. We can get an empirical estimate for the flux of the radiocarbon from the stratosphere to the troposphere, and as well as the global production rate. Okay, that correlation of radiocarbon of CO2 with N2O that I keep showing you, that looks so nice linearly, right, above 200 ppb of N2O. From that, we're going to be able to calculate the radiocarbon flux because we know what the N2O loss rate is. And here's how we can do that if you're not familiar with this already. Plum and Co. and Plum in 2007, right? We know that two tracers that are long-lived with respect to vertical and quasi-horizontal transport will exhibit a compact relationship. We've been talking about that already, right? And so, right, one of the reasons is they have similar concentration, they have similar isopleths, right, in these 2D models. These are satellite observations of methane and N2O, and this is where some of these ideas came from, were some of the early satellite measurements, right? So things that their chemistry may not even be related, if they're simply long-lived with respect to vertical and quasi-horizontal transport, you'll get a straight line, okay? And that straight line is very important, okay? Not just because it makes our lives easier for looking at trying to compare in situ measurements, low time and spatial resolution in situ measurements with global models, right? But we also, that slope of that relationship is simply the ratio of the net vertical fluxes of the two species. And Plum in 2007 showed you can just get that from the surf zone. It doesn't have to be a globally consistent tracer-tracer relationship. So from that line then, right, well, we know independently what the net vertical flux of N2O is in the stratosphere, right? We know what that is from satellites and from modeling. And this has been used before. I've used this before. Other people have used this relationship. The slope of the tracer-tracer correlation is equal to the ratio of the net vertical fluxes. This has been used to estimate global mean cross-tropopause fluxes for ozone, for nitrogen oxides, meteoritic material, and I've used it a lot for N2O and CO2 isotope logs as well. Okay, so we're going to apply this then to the radiocarbon and see what we get. Yeah, the Rockies are plain. We'll sort of skip this, right? We got the net vertical flux. We got the slope, right? You might need an air mass flux. If it's like CO2 that the concentration difference isn't too much, it just all cancels out. But in addition, for tracers like N2O and methane, if the air mass flux were larger than you thought, right, then the isotopic composition of the enrichments in the heavy isotopes can't build up as much. So the product of the isotopic composition and the flux, the isoflux, is the same, right? So if you slow it down, then the isotopic enrichment is higher, and the product is the same. So guess what? We don't really care where you define your tropopause, since it can't really be defined anyway, right? We don't really care because it all comes out in the wash within the uncertainties that we're interested in. Okay, so that's how we're going to get that. I'm just going to give you the numbers. So, right, from this region in the extratropical lower stratosphere, then we can take the slope of these lines. We know what the N2O loss rate is, right, which is the net vertical flux of N2O, since the loss of N2O is all in the stratosphere. So we can get a net radiocarbon flux from the strat to the trope, the net of units and numbers that only an isotope geochemist could love. Okay, all right. So I don't know if that means anything to you. I always have to look it up. This is in per mole of CO2 per year. Okay, but from that, right, we can also say, well, this is the production rate it's basically the production rate in the stratosphere, right? Since the radiocarbon production rate in the stratosphere is half of global, half of it's in the stratosphere, half of it's in the upper troposphere. There might be some uncertainty to this, but this is what all the radiocarbon people use. Then the global annual mean production rate of radiocarbon, right, is 2 times that. And these are units that the radiocarbon production people love. All right, so you have to be really flexible in your units, thinking about them. 2 times 10 to the 26 atoms of radiocarbon per year. Okay, so that's our number empirically. It's really the highest uncertainty to this is in part the how good our tracer-tracer correlation is and how many data points we have, as you'll see in a minute, as well as the uncertainty. That's a systematic uncertainty in the N2O loss rate. Okay, so how does this compare? So here's our global mean radiocarbon. That's from this study. Fortunately, if we put in, right, we've got the production rate in the model, implemented in the model, we'd better be able to get that back out from a Plum and Co analysis from the N2O and radiocarbon that we've got. It's a little bit more uncertain because there aren't many points down low, but we get out what we put back in as well. That's nice. But it's also interesting to compare how other methods of calculating this from the complex cascade of elementary particles. There's all this physics, right? You've got to track these particles down from the all the way through the atmosphere until the energies are just right for them to be captured by a nitrogen-14 nucleus, right? And then there's a 25% uncertainty just in those capture cross-sections. Maybe those need to be measured again, right? So there's a lot of we've got an N2O loss rate uncertainty of 25%. They've got a thermal neutron cross-section comparison, as well as this cascade through the whole atmosphere. So I think it's pretty interesting to compare some of these. So all these that are calculated from this cascade and the nuclear physics of that. The ones that say inventory are looking at the redistribution, right? So you need to make some assumptions about the size of the reservoirs, right, et cetera, over time. All really valid, but I was really excited to say, hey, I've got radiocarbon, I've got N2O. Here's a global production rate simply from that, okay? And so here's a comparison. It's a little more, I've got this in order of time, so let's just plot this versus year of publication, all right? Okay, so here's the radiocarbon production rate versus year of, right? There's a significant trend. There's definitely a significant trend. It's not really clear in the inventory papers, right, why there's a trend, just magically the numbers sort of decrease. I think as they probably have more data and understand more about the residence times and inventories. And here's our data point here. This is a particle physics calculation in which they updated the cross sections for the alpha particles and the protons in addition to the neutrons. So anyway, everybody's kind of coming down this way too, but this production rate is becoming more and more important as the cosmogenic production rate and stratospheric exchange is becoming more and more important as the radiocarbon is actually pretty much out of the atmosphere, but it's going to start coming back out of the ocean. So what's the stratosphere and what's stuff? Old radiocarbon coming out of the ocean is going to be important. There's a solar max. I'm going to speed it up because it is you guys need an update on the Rockies game, and it is Friday afternoon if you're not a baseball fan. So there is, though, one thing I want to point out here. There is an 11-year solar cycle in the production rate. Okay, so that's because when there's high solar activity and high solar wind, that actually deflects, if you will, probably not what a physicist would say, but that deflects the incoming cosmic rays. So that means there's an anti-correlation between solar activity and the radiocarbon production rate, okay? And so we put in the model of plus or minus 10% everywhere, which should be an upper limit to what we thought that solar to what we thought the solar cycle dependence is of that radiocarbon rate. And our measurements that we did are about mid-solar cycle, okay? And then again, different groups and different calculations come up with different values for that. So, yes. All right, so it just so happens though, if we have this time series of data, we have about a solar cycle. It's not evenly distributed, but we have about a solar cycle of data. So we went through this to see if we might see any information on whether we might see a large solar cycle or not. Okay, so we took the global annual mean net flux to the stratosphere. We doubled from the troposphere to the stratosphere. That's here. We doubled that to get the global annual mean production rate. This gray area here was the numbers that I had just shown you. Okay, this actually doesn't match a solar cycle. I think it's just noise, okay? So I didn't put a solar cycle on here. That kind of irritated the reviewers of the paper that's been submitted to JGR. This doesn't exactly match it. In part, we think this is just noise. In part, that's because, so we don't see any obvious, no, as yet, obvious dependence on the solar cycle production rate. One argument is these may just be noise. They are the dregs of our old mission, right? We pulled these, there's nothing wrong with the samples, but we only had a handful left. And they're from different latitudes. That's not how you would want to map that out if we'd been doing this on purpose. We're just glad we could go back and we had these samples in stored glass ampules, CO2 purified in drawers, right? And so, right, here's n equals 7, n equals 10. We think that's where, and this wouldn't match what we would expect anyway from the timing from actually being a solar cycle. But here, this is the Seeker's data. I'm going to show you this really quick. We have 50 samples from here, so you can see the uncertainties are much smaller there, the precision. We're not, I'm going to skip this, it's the Rockies game. If we just do a back of the envelope calculation, a 10 to 30% solar cycle, there's this production rate, but it's going into this vast reservoir, into the stratosphere, and then the troposphere's pumping stuff in. If we just do an analytic solution to those equations, we would only expect about a 1% modulation, right? Just because it's going into a large reservoir, all right? So this remains to be determined. We do have, for the people doing inverse modeling of radiocarbon, this is from Seekers. This is 15 north to about 50 degrees north. We have these beautiful vertical profiles across the tropopause. And this is in part, then we can test, is there latitude dependence? Is Plum right from 2007? Does it really matter where they are as long as we have enough points to not be noisy? And in fact, from this analysis, we can see that there's not really a latitude dependence, and we're getting the same answer through the whole northern hemisphere. So the fact we don't, so it's robust with latitude, and it's robust as long as we have a larger n. So we're not seeing an obvious solar cycle. We don't really expect to see one. The age spectra are large, the reservoirs are large, and to the extent that we can get larger n in the future, I think we could map this out. But I think the fact that we don't see a solar cycle dependence is one more headache that I hope is out the window, right? That we don't have to worry about that, because I really want the largest determinant of the radiocarbon, right, to be the residence time and to reflect the circulation rather than a solar cycle, which you could correct for, but I would rather not, okay? I imagine the modelers would agree with me. All right, so this is my summary slide then. I am just about done. I've shown you the first extensive post-bomb era stratospheric radiocarbon measurements. It's a unique inert tracer of stratospheric transport and residence times. It's actually really what we wanted back in the day, right? For high-speed civil transport, a commercial flight of supersonic aircraft putting all their NOx and other emissions, right actually where the production rate of radiocarbon is in the lower stratosphere, right? So a tracer, that's exactly what we wanted to know then, and what funded a lot of that old look at the old era in the stratosphere was what would the impact of a huge fleet of commercial supersonic aircraft be. And I feel like these have been brought to fruition by our modern ideas of tracer-tracer relationships. How can we compare these sparse in situ measurements with global models, okay? I think we've set new benchmarks for modern stratospheric residence times over time to try to answer the question, is the stratospheric circulation is accelerating as climate changes, and maybe with a different dependence than the mean ages at 25 to 30 kilometers have done, where, you know, maybe that's a node where the mean ages aren't changing much, and the circulation is changing in other ways that we need to inform with additional measurements. And then the last part was these empirical estimates for the global annual mean radiocarbon production rates and net fluxes to the troposphere that are needed for carbon cycle studies, okay? And again, as the bomb radiocarbon has moved out and redistributed, it actually matters now what the cosmogenic radiocarbon flux is from the stratosphere to the troposphere. The stratospheric transport does matter. It's annoying. It's really annoying, but it actually is going to matter when you're in Los Angeles or La Jolla or Göttingen in Germany if you're trying to take radiocarbon measurements at the surface and trying to figure out what the emissions are. You're going to need to take stratospheric transport more and more into account, and that's only going to be more and more important into this next century, okay? Along those lines, for people interested in the modeling of this, I can give you the annual mean stratotrope radiocarbon flux. Boom, you got it, you saw it, okay? That doesn't mean that's going to allow people to take the stratospheric signal then out of their surface measurements, because there's a seasonality to that, and an El Nino dependence, and stratotrope exchange, and you know, if you're sitting in La Jolla and in an El Nino year, you might or might not have stratospheric air come your way because tropospheric transport is changing, for example, with an El Nino. So that's going to require 3D models, maybe some mean age of tropospheric air type of models or green functions for the troposphere to take the annual mean flux, right, from the radiocarbon stratosphere and get that CO2 signal out of there. Oh, look, Malwarebytes is telling me that I need to end now. I've never gotten that before. Thank you, Malwarebytes. All right. All right, it's telling me to move on, and so that is my thank yous. This was funded by NASA's Upper Atmosphere Research Program over many, many cycles. Thank you. Malwarebytes, you're covering up my Lawrence Livermore. Here, let's see. We can close. All right, and UC Lab Fees Program and IGPP. Amadou Kanu did the modeling at Livermore, and Lauren Garofalo is now a postdoc in Delphine Farmer's group at Fort Collins. I'll get to see her next week, so I'm excited about that. She did all the new measurements, the 150 new measurements. And of course, my whole air sampling colleagues. Thank you. I'm going to get Terry for 20 years of helping me do science at my UC Berkeley lab without living in a hotel. Thank you very much. And to Tom Gilderson of the radiocarbon measurements and Philip Cameron Smith for the impact lead. Okay, and thank you very much for your time on a Friday afternoon.